Swayam Prabha. Digital India. Educated India.
Some examples of artificial neural networks. Now, we have seen how to design an artificial neuron by copying the principle of a biological neuron. We have also discussed how to form a layer of neurons, and we have also seen how to design a particular structure of artificial neural networks. Now, we are going to discuss some of the very important and popular neural networks. So, we are going to concentrate on the working principle of a few networks. Now, these networks are as follows. We are going to discuss the principle of multi-layered feed-forward neural networks. Then we are going to concentrate on radial basis function networks. After that, we are going to concentrate how to include the feedback circuit along with the feed forward circuit to develop the most popular, that is the recurrent neural networks. We will see the principle of self organizing map or coherent network, and at the end we will try to see the working principle of a counter propagation neural network, and we will solve a few numerical examples also. Now, here actually let me start with the first one, that is your multi-layered feed forward network, and in short this is known as your MLFFNN, that is multi-layered feed forward neural network. Now, its name indicates that this particular network consists of a number of layers, and here we are going to consider 3 layers, that is the input layer, then comes hidden layer, and we have got the output layer. Now, here on the input layer we are going to consider capital M number of neurons. Similarly, on the hidden layer we have got capital N number of neurons, and on the output layer we have got capital P number of neurons. So, this is known as in fact your MNP networks. Now, here if you see on the input layer we are using the linear transfer function, say it is something like y equals to x sort of thing, and we have considered the slope of this particular the straight line, say m, that is equals to 1. So, on the input layer we are considering the linear transfer function y equals to x. On the hidden layer we are considering the log sigmoid transfer function, and we have already seen the mathematical expression for the log sigmoid transfer function, that is nothing but y equals to 1 divided by, so 1 plus e raised to the power minus a x. Now, here so this particular a is actually the coefficient which is going to decide what should be the slope of this particular the curve. Now, this I have already mentioned that the higher the value of a, the steeper will be the curve, and vice versa. So, this is the log sigmoid transfer function, and it varies from the output varies from your 0 to 1. Now, on the output layer we consider the tan sigmoid transfer function, and if you see the mathematical expression for a tan sigmoid transfer function, this is something like this. So, y equals to e raised to the power a x minus e raised to the power minus a x divided by e raised to the power a x plus e raised to the power minus a x. So, this is nothing but the tan sigmoid transfer function, and once again the coefficient A indicates the slope of the curve. Now, if you see the range for this particular the tan sigma transfer function, it varies in the range of -1 to +1. So, this is regarding the different types of the transfer function used in the different layers of this particular the network. Now, then comes your the connecting weights between the input layer and this particular your hidden layer is denoted by the V matrix, and similarly the connecting weights between the hidden layer and the output layer are denoted by, so this particular the W matrix. And if I see the individual values for these connecting weights, it may vary in the range of say 0 to 1 or in the range of say -1 to +1. That means, these are in the normalized scale. Now, here if you see the inputs, as I mentioned, there are m inputs, and actually on the input layer we have got the m number of neurons. Now, let me concentrate on a particular neuron lying on the input layer, say ith neuron, and a particular neuron that is your the jth neuron lying in the hidden layer, and a particular neuron lying on the output layer, say this is nothing but the kth neuron. So, the connecting weight between I and j is denoted by your V I j, and the connecting weight between your j and k, this is nothing but is your W j k. Now, I am just going to discuss little bit like how to your how to design in fact your how to send the inputs to this particular the network. Now, remember one thing. So, the inputs to the neural networks are sent in the normalized form, because the different inputs may have different ranges, and if you do not normalize, there could be a possibility that this particular network may not work properly. So, what you will have to do is all the inputs like your, so these inputs you will have to pass in the normalized scale. Now, before that, if I how to make it normalize, so I am just going to discuss in details. Now, before that, let me just tell you one notations which I am going to use here. Now, this I1, this particular notation indicates the input of the first neuron lying on the input layer. Then comes your I01 is nothing but the output of the first neuron lying on the input layer. Similarly, if I see, so this Hij is nothing but the input of the jth neuron lying on the hidden layer. So, Hoj is nothing but the output of the jth neuron lying on the hidden layer, and this Oik is nothing but your the input of the kth neuron lying on the output layer, and this Ook is nothing but your output of the kth neuron lying on the output layer. Now, I am going to discuss how to make, so these particular inputs in the normalized scale. Now, normalized scale means either we will have to put in the scale of say 0 to 1 or in the scale of say -1 to +1. So, let me discuss how to make it in the scale of say either 0 to 1 or from -1 to +1. Now, let me concentrate on this first one, that is I1. Now, to represent in the normalized scale, that is 0 to 1, the formula which we generally use is something like this, that is I1 minus I1 minimum divided by your I1 maximum minus your I1 minimum. Now, if I put that I1 is equals to your I1 minimum, so I will be getting which is nothing but 0, and if I put that I1 is nothing but I1 maximum, so I will be getting 1. So, this is the way actually. So, this particular input is to be converted in the scale of 0 to 1. Similarly, if I want to represent in the scale of -1 to +1, so what I will have to do is actually I will have to use one expression which is nothing but 2 multiplied by. So, this particular expression, that is 2 multiplied by I 1 minus I 1 minimum divided by I 1 maximum minus I 1 minimum minus 1. If I put I 1 is equals to I 1 minimum, so I will be getting 0 here, that means I will be able to generate minus 1. And if I put I minimum equals to I 1 maximum, so here I will be getting 2 minus 1. So, this is nothing but plus 1. So, I can vary this particular input in the scale of -1 to +1. Now, the point which I am going to make, that these particular inputs are to be represented in the form of normalized scale. And once you have got this particular the inputs in the normalized scale, and if I use the linear transfer function on the input layer, so I will be getting the output that is nothing but equal to the input. That means, your IOI will become equals to I. So, this is the way actually we can find out the output of the neurons lying on the input layer. And once you have got, so these particular outputs of the first layer, now I can multiply with the corresponding connecting weight, and I can sum them up, so that I can find out the input for the hidden layer. And once you have got this particular input for the hidden layer, it will pass through your the log sigmoid transfer function. So, I will be getting the output like HOJ, HO1 and so on. And once you have got these particular outputs, now we will multiply with the corresponding connecting weights denoted by W, and those are summed up here, and that will be the input of the kth neuron lying on the output layer. And once again it will pass through the transfer function, that is your 10 sigmoid transfer function, and accordingly I will be getting the output of the kth neuron lying on the output layer. So, this is the way actually we can carry out the forward calculation, and we can find out what should be the output for a set of inputs. Now, here before I go for the forward calculation, I am just going to mention two things. One is we generally use some bias value. So, we put some bias value, but here for simplicity actually I have assumed that bias is equals to 0. And this is actually how to make this particular analysis little bit simpler. Now, another thing I should mention, that initially we generate all such connecting weight values like the V values and W values at random using the random number generator, and then through a large number of iterations we try to find out what should be the updated values for this V and W, so that this particular network can make the prediction as accurately as possible. Now, let me repeat once again, for the set of inputs, and if I know all the transfer function and the connecting weights, so I will be able to find out, so this particular the output, and this is nothing but the calculated output. Now, for this training scenario, that means for this set of input parameters, there is one known output, and that is nothing but the target output. That means, if I write here, so OOK is nothing but the calculated output of the kth neuron lying on the output layer. I can also write down, so TOK is nothing but the target output of the kth neuron. Now, if I know the target output, so very easily I can find out the error. How to find out? I am just going to discuss in details, and once you have got this particular error, by comparing the calculated output with the target output. So, this particular error I will propagate in the backward direction, and so that I can modify or I can update all the connecting weights, and I can update the coefficient of the transfer function, and through a large number of iterations I am just going to do this particular updating, and ultimately, so this particular network is going to make the prediction as accurately as possible. Now, another thing I should mention, that the performance of this particular network depends on a number of parameters. For example, it depends on the connecting weights, it depends on the coefficient of the transfer function, whether it is log sigmoid, tan sigmoid, or whether it is the linear transfer function, it depends on the slope of the linear transfer function. It also depends on the topology or the architecture of this particular network, and to represent the topology or the architecture, we see how many layers are there and how many neurons are present in each of these particular the layer. So, the performance of this particular network not only depends on the architecture or the topology, it also depends on the connecting weights, the coefficient of transfer function, and all such things. Now, let me see how to carry out actually the forward calculation for this particular the network. Now, before I go for that, this I have already mentioned that this V is nothing but the connecting weights between the input and the hidden layer, and this is actually a matrix, the matrix of connecting weights, and here this is nothing but one m cross n. So, this is nothing but actually m cross n matrix, and this particular W matrix is the connecting weight matrix between the hidden and the output layer, and this is nothing but is your n cross the P matrix. Now, as I told that initially these are generated at random and through a large number of iterations. So, these particular connecting weights will be updated. Now, let us see how to carry out the forward calculations. Now, step 1, we try to determine the output of the input layer. Now, as we have considered the linear transfer function of the form y equals to x. So, output equals to input. So, we can very easily write down the output of the ith neuron lying on the input layer is nothing but the input of the ith neuron lying on the input layer, and here small m is varying from 1 to up to capital M. Now, once you have got the output of the input layer, now we are in a position to determine what should be the inputs of the hidden layer. So, we are going to discuss step 2, and the input of the hidden layer, that is nothing but Hij, that is the input of the jth neuron lying on the hidden layer is nothing but V1j multiplied by I01 plus there are a few terms, the middle term will be your Vij multiplied by Ioi plus dot 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 plus the last term Vmj multiplied by Iom. Now, here j varies from 1 to up to n, and once you have got the input of the hidden layer, now it will be passed through the transfer function just to find out what should be the output of this particular the hidden neuron. Now, let us see how to find out the output. So, step 3, that is the determination of output of the hidden neuron, that is Hoj is nothing but the output of the jth neuron lying on the hidden layer is nothing but 1 divided by 1 plus e raised to the power minus a1 Hij. So, Hij is actually nothing but the input of the jth neuron lying on the hidden layer, and this particular a1 is actually the coefficient of the transfer function. Now, next is the step 4, that means we will have to find out the inputs of the output layer. Now, this Oik is nothing but the input of the kth neuron lying on the output layer, and that is nothing but W1k multiplied by H01 plus there are a few terms here plus Wjk multiplied by Hoj plus there are a few terms here, and the last term is your Wnk multiplied by Hon, and k varies from 1 to up to capital P, and this P is nothing but the total number of neurons lying on the output layer. Now, this is the way actually you can find out the inputs of the output layer, and once you have got the input of the output layer, now in step 5 we allow this particular input to pass through the transfer function, and you will be getting actually OOK, and that is nothing but e raised to the power a2 OIK minus e raised to the power minus a2 OIK divided by e raised to the power a2 OIK plus e raised to the power minus a2 OIK, and this a2 is nothing but the coefficient of the transfer function. So, this OOK is nothing but the calculated output of the kth neuron lying on the output layer, and once you have got it, now we can compare with the target value, that is the output of the kth neuron, that means your the target output, that is denoted by TOK. Now, if I have got the target output is nothing but TOK and the calculated output is nothing but OOK. Now, this particular thing it could be either positive or negative, and that is why to make it positive what we do is either we consider the mod value of this, or what we consider is your like TOOK minus OOK. So, square of that just to make it positive, and here you can see I have added here one term, that is your half. So, this is multiplied by half. The reason is actually very simple. Now, in future, so I will have to differentiate. So, this particular your the error of the kth output neuron with respect to the calculated output, and there if I put square here and if I differentiate. So, here I will be getting 1 2. So, this 2 will be multiplied by half just to make it 1. For this particular purpose actually we use this particular term, that is half. So, we are able to find out what should be the error of the kth neuron lying on the output layer, and that is nothing but half TOK minus OOK. Now, once you have got, so this particular the output of the kth neuron lying on the output layer. Now, in the output layer in fact, we have got a large number of neurons or say p number of neurons. So, I can find out what should be the total error of all the neurons lying on the output layer, and that is nothing but E is summation k equals to 1 to capital P half TOK minus OOK square. So, this is nothing but the total output of the output layer considering p neurons. Now, if I have got this particular total error, that corresponds to in fact only one training scenario. That means, only one set of inputs and outputs, and supposing that we have got say capital L number of training scenarios. So, what we will have to do is we will have to pass all the training scenarios one after another, and we can find out. So, the total error after passing all capital L training scenarios, and that is denoted by E total. So, E total is nothing but summation L equals to 1 to capital L, summation k equals to 1 to capital P half TOKL minus OOKL square, where capital L indicates the number of training scenarios. Now, here, so this particular term OOKL represents the output of the kth neuron lying on the output layer corresponding to Lth training scenario. Similarly, so this particular TOKL indicates the output of the kth neuron lying on the output layer, and this particular output is the target output corresponding to the nth training scenario. So, this is the way actually you can find out what should be the expression of the total error for this output layer neurons after considering all the training scenarios. And once you have got this particular picture, now we are in a position like how to propagate it back, so that we can modify actually your the connecting weights and the coefficient of transfer function, so that this particular the network can make the prediction as accurately as possible. Now, here actually I am just going to discuss now how to minimize this particular the error in prediction. Now, this to minimize the error in prediction, so what you will have to do is we will have to take the help of one optimizer or one optimization algorithm. Now, here I have already discussed that the performance of this particular network depends on a number of parameters. So, if I consider this error in prediction of the network, so that is a function of so many variables. For example, say it depends on the connecting weights V, it depends on the connecting weights W, it depends on the coefficient of transfer function say A1, it depends on the coefficient of transfer function A2 for the output layer, it also depends on the slope of the linear transfer function say M, and there are a few other parameters. So, it depends on in fact a large number of parameters. Okay. Now, what I do is for simplicity, for the purpose of explaining how can it be minimized, how can this particular error be minimized. So, what I assume that this particular error is a function of only two variables, one is V, another is your W, and for the time being you just forget the other terms. And if I express that this error in prediction is a function of two variables V and W. So, very easily we can prepare the plot, and that plot is nothing but the error plot, and we will be getting this particular the error surface. Now, if I plot, so this particular error along the z direction and say the connecting weight V along x direction and the connecting weight W along y direction. So, I will be getting this particular the error surface in 3D. Now, we know that we human being can visualize only up to 3 dimension, and that is why we have considered that this particular error is a function of only two variables. So, that we can plot this particular error surface in 3D. Now, if I consider more, so it will become 4 or more than 4 dimension, which we cannot visualize. So, let us assume that this error is a function of only two variables. So, on the 3D plot, so I can see what should be this particular the error surface. Now, as I told that we start with the random values for this particular the V and W, and supposing that initially the error of the network is here say, and what is our aim? Our aim is to reach the minimum value of error, which is here. So, what I do is we start from here, then through a large number of iterations actually we try to move towards the minimum error solution, and gradually. So, during the training the network is going to reach this particular state, so that if we send a set of inputs, it will be able to predict the output as accurately as possible. Now, as I told that we are going to take the help of some optimization tool. For example, say we are going to use a very popular optimization tool, the traditional tool for optimization, that is known as the steepest descent method. So, this steepest descent method actually we are going to use. Now, this steepest descent method is one of the most popular the traditional tools for optimization, and here the search direction is opposite to the gradient. So, we try to find out the gradient direction of the objective function, and try to move in a direction opposite to the gradient. The same principle actually has been copied here in back propagation algorithm. Now, here actually what we do is we try to find out the change in V, that is the connecting weight between the input and the hidden layer, that is nothing but minus eta multiplied by the partial derivative of error E with respect to the V. So, delta V is nothing but minus eta multiplied by del E del V. Now, this particular actually the eta is known as the learning rate. Now, this learning rate actually it varies in the range of say 0 to 1. Now, if I compare, so this particular expression with the expression of this particular the steepest descent method. So, the search direction is decided by minus del E del V, that means I am moving in a direction opposite to the gradient, and here. So, this eta, that is the learning rate, is going to represent actually the step length of this particular the steepest descent algorithm. Now, let me mention that for any optimization tool, there are two things which you will have to consider. One is your what should be the search direction and what should be the step length during the movement. Now, the same thing we just copy it here to find out the change in V is nothing but we consider that eta is nothing but the step length and minus partial derivative of E with respect to V. So, that is going to decide what should be the search direction. Now, similarly, actually the change in W is nothing but minus eta del E del W. Similarly, if I just want to say find out the updated value for this the coefficient your A1, A2. So, what you will have to do is, so you will have to find out what is change in A1, and that is nothing but minus eta partial derivative of error with respect to this particular your A1, and similarly I can also find out the small change in A2 also. So, this is the way actually we can implement this delta rule just to find out what should be the updated values for the connecting weights and the coefficients. Now, I will be discussing all such things in details mathematically. We will see how to determine. So, these updated values with the help of some your mode of training, and those things will be discussed in details. Thank you.